Hi, can you hear me? Oh, I actually cannot hear you.
Can you hear me?
Yes, yes. Oh, yeah, you have to give me share rights to share my
Oh, sorry.
screen.
Give me a second. Can you try now? We good? So I think I will introduce you,
Okay,
and after like 2 minutes, you can start.
okay,
Yeah,
yeah. Just let me know. But you can see my screens, right? Everything's good over there.
we can see his screen, right? Yeah.
Cool, cool.
Just so you know, we have over 100 people here, and
Oh,
wake up
wow.
very early in the morning. Yeah. All right. So,
Okay, yeah. Just let me know when to start. Yeah, I'm ready.
all right. So I will introduce you now. Right.
Okay.
So hi everyone. Thank you back for the section, and thank you all again for waking up so early. So we have Dr. Pingyu Chen today from IBM Research and MIT IBM Lab as a principal research scientist in the Trustworthy AI group. So Dr. Chen was trying to be here, but he is receiving his EJK Computation and Software World, which is a highly contemporary work also work by to Andre N before. So he's in EJK now, and to sharing his word talk. A lot of work about his talk will be also featured in this interspeech tutorial. So yeah, kind of a world level is like tutorial here. So Dr. Ping Chen received his PhD from University of Michigan with Professor Afelo Hiro. So he has been working in IBM, has been how many years, Ping?
Like 7 years.
7 years. Yeah, has been 7 years and received a lot of fast paper award and some pioneer award before. So let's welcome Pingyu for his talk on the second pass of the tutorial for multimodal learning in the era of foundation models. Please, Pingyu.
Yeah, so hi everyone, this is Pinyu, and thank you, Hug, for a nice introduction. And apologize again for not be able to be there with you because of the conference travel schedule conflicts. So I'm not able to see you guys, but if you have any questions, and then feel free to inform Hug, and then we can stop anywhere to have a deeper discussion. Okay, so in this session, right, we'll be talking about trustworthy AI and cross-modal learning based on foundation models. So foundation models, right? I think most of us are pretty much familiar with this term now, right? So it's basically describing a new and very exciting pattern that we have been observing in machine learning, which is basically training a large and complex foundation model to represent different data formats, right? Name it images, name it text, name it audios, doesn't matter. We just use train a large neural network, right, to encode these different data modalities into a continuous numeric vector representations. And with that generic representations, we can take the representations and fine tune this model to solve different downstream tasks using labeled data or even like feature learning, supervised learning, and so on, right? And one of the most successful example of foundation model nowadays, right, is ChatGPT, right? So ChatGPT is a fine-tuned version of the foundation model, GPT-3 or GPT-4, right? Fine-tuned on question answering data to become a chatbot. So foundation models are in general, right? In this talk, we will view it as powerful models that is pre-trained on large-scale data sets. I would like to quote Sir Isaac Newton here, right? So he once said, "If I have seen further, it is by standing on the shoulders of giants," right? So here, I believe this pretty much will describe the success we have been seeing in foundation models. Here, giant is the foundation model, and the person who is standing on the shoulder is basically leveraging the foundation model to see further and do more and make further advancements. So, and pre-trained models here, right, can be pretty much those models trained on data-rich domains, right, like text, image, and speech. But there are still challenges in some domains, right, like we call low resource or resource limited domains. And by low resource, we mean those domains with limited data, right? Like for example, medical data or molecular learning problems where getting high quality data or getting annotations for those data are actually very challenging, right? Or like some new domains where just training a high quality pre-trained model is very difficult due to limited computing resource or limited data available in that particular domain. Also, there could be some other constraints that will lead to this low resource training scenario. For example, a very tight data privacy budget, which means you cannot access the data too many times to train good representations, or some training time constraints, right, limited by computing resources you have. So in these scenarios, right, we are interested in looking for some resource efficient fine-tuning or transfer learning approaches to maximally leverage pre-trained models from alternative domains to solve the target domain, right, the domain we are interested in. And that will be a powerful technique that we call the reprogramming to reuse these models to solve the task that we are interested in without tuning the model. So this is what we call model reprogramming, right? So we start from a pre-trained model in a specific domain, and different from typical fine-tuning approaches, right? In the process of fine-tuning the model, we are actually not changing the weights of the model. And instead, we are adding 2 layers to this pre-trained model at the input and at the output, what we call the input transformation layer and the output mapping layer, to adapt the pre-trained model to solve different downstream tasks. And in this talk, we will show you some of successful examples of how this cross-modal learning works, right? For example, reprogramming a speech model to solve time series learning problems, reprogramming a language model to solve molecular learning problems, or reprogramming a computer vision model to solve biomedical learning problems. And the key here is really about parameter efficiency and reusability, right? So the size of the pre-trained model can be pretty huge, but if you use model reprogramming to adapt it to solve the different tasks, we actually only need to train the layers that we introduced, by the blue and green layers that I show on the left here. So in terms of number of trainable parameters, right, it actually can be made very parameter efficient. And also we will show that in terms of the data you require to fine-tune this model to achieve good performance to a downstream task, it can also work pretty well in terms of the data scalability perspective. And I also actually wrote a survey paper which is available on arXiv about this model reprogramming, which is what I'm going to show you today in this tutorial. So foundation models are what are the key features of the foundation model. So basically, today's foundation model has several key features, right? The first thing is it needs to train on a large-scale data set for pre-training to obtain a good representation of the data. For example, for text, right, we basically trained our today's language model using the entire web-scale data set, or like Wikipedia, the entire Wikipedia, right, to be able to have a good representation of words, tokens, and so on. And we also need to make sure the neural network has have high capacity, which means it has to be large and has to be deep, and also transformer-based architectures. And once you have that, right, we'll train a foundation model at scale, right? We can efficiently take that model to fine-tune a different downstream task. So one typical example is GPT use cases, right? So for example, the backbone of the ChatGPT model, like GPT-3, it was actually trained on a corpora with about 1,000 billion tokens. And the total number of trainable parameters of GPT-3 is about 175 billion. The size of saving that model, right, is about 350 gigabytes. And if you use a cloud resource to train a model, it probably takes about 12 million to train such a model. So it's certainly reasonable that because training these foundation models are so costly, right, it makes sense to think about how to reuse them to solve these different tasks as much as we can, right, given the resources we put into training and tuning those models. And that is only for GPT-3, right? So if you now go to the era of GPT-4, right? So although it was never be made public that how pricey the GPT-4 is, right? But anecdotally, right, the CEO of OpenAI, Sam Altman, actually admits that the training cost of GPT-4 could be above 100 million, and if not more. So okay. So how do we use combine these foundation models and reprogramming together? Right? Basically, we are interested in consider the resource limited setting. And as I already described, right, in the standard setting where you have abundant training data, abundant compute resources, right, you may just want to do machine learning in a typical way, right, the pre-training and fine-tuning strategy, right? However, in a resource limited setting, right, you may want to try this reprogramming setup, right? Which means we are going to insert some new layers, right, to fine-tune the model, right, instead of fine-tuning the weights itself, right? And also, especially in the scenario where you are solving a problem in a new domain with limited data and limited compute resource, right? And for example, the low resource time series classification problem or low resource speech learning problems as an example. And the interesting idea is that we don't need to limit ourselves to use pre-trained data in the same domain, right? So because pre-trained models exist in other domains, right? So reprogramming allows you to do what we call the cross-modal or cross-domain machine learning by leveraging pre-trained models built for other domains to solve the problems we are facing in our interested domain. So there is a very clear distinction between standard transfer learning versus reprogramming. So in standard transfer learning, right, we are basically take the weights from the pre-trained model in the source domain, and then we take the data from the target domain, and then we choose to fine tune a subset of the parameters in the pre-trained model, right? For example, the last few layers weights, right, when we fine tune the source model to the downstream task. On contrary, right, model reprogramming does not change the pre-trained models at all, right? So we inserted new layers instead of fine-tune the weights associated with existing layers. And this feature allows us to do cross-domain learning in the sense that we can take pre-trained model from domain A and solve a different tasks in domain B. And we can also show empirically and theoretically that doing so can actually brings a lot of benefit in terms of data and compute efficiency and achieve state-of-the-art performance. Any question before I move on? Okay, I'll continue. So before we dive into details, I would like to give some background in terms of where this idea of reprogramming coming from. So the first paper talking about this reprogramming idea is actually motivated from this adversarial perspective, right? So in the paper actually published in iClear back in 2019, they have this idea of adversary reprogramming a model, right? So in their study, they showed it is possible to take an ImageNet model, right, and then do something magical, like without changing the model weights, but reprogramming an ImageNet model to be able to solve like MNIST and CIFAR-10 or some like shuffled MNIST classification task with reasonably good accuracy, right? So you can see we can reprogram the ImageNet model without fine-tuning the weights to have a MNIST accuracy about the 0.97 or 0.96, which is not great, but okay, right? But the interesting thing is that they motivate this reprogramming idea by saying it can lead to a new type of attack, right? By reprogramming a model service provided by some model developers, right? By secretly reprogramming the model to solve something or some tasks that were not designed or that were not considered by the model developers. So there were some concerns about the ethics or the risks of a model being reprogrammable to solve different tasks, or stealing some models' performance, right, or capacity to solve a new task without the consent of the model developer. But the accuracy were not really good in terms of the experiments they carry out. So we kind of take this idea and explore further, right, in this era of foundation model, right? So, well, how much we can maximally leverage foundation models with reprogramming, and in what setting, right, will the reprogramming be most beneficial? So I would like to use this example of image classification task first, right, to walk you through an example of model reprogramming. But and then we will show this actually can be extended to different scenarios because it's a very generic approach. So again, the setting here is that we start from a pre-trained model, right, and then it can be a white box model or a black box model. So white box model means the pre-trained models, right, is transparent to us, right? We know the architecture, we know the pre-trained weights and so on. But reprogramming also works even if the model is a black box model, which means it could just be an online API, and then we don't know the weights and architecture, right? Like a ChatGPT-4, right, for example. Sorry, ChatGPT, right, not ChatGPT-4, for example. So it's an API, we can call the API to generate predictions and so on, but we never know as a user what is the model and architecture behind ChatGPT. And then we would like to take this pre-trained model and reprogram or repurpose the model, right, to solve some new tasks, right, that were originally not designed for the source model to solve, right? For example, here we are trying to reprogram image classifier, right, trained on general image classification to solve some biomedical associated images, right, like melanoma classification or ASD, autism spectrum disorder classification tasks. These are all like medical imaging classification tasks. So let me show you an example of how this reprogramming works in the image domain, right? So we start from a pre-trained image classifier, for example, a model that was pre-trained on ImageNet data, right? So it will take an image and generate a prediction over the space of the classes that we have assigned in ImageNet data. Now we have given a set of target domain data, right? For example, these medical image examples and data sets. So what we will do is there are three key steps, right, to enable reprogramming. The first step is what we call visual prompting, right, or input transformation. So what we will do is we will put the target data, right, at the center of the data input, and then we allow some space for these extra pixels, right, or more generally like tokens that are assigned to be universal and trainable when we do model reprogramming, right? So this is for reprogramming the target data, right, to adapt the model to be able to solve the target task, right? So this gray area, right, is actually some pixel values that was actually preserved and actually appended to every target data, and it's also universal to every target data. And then we will make this region trainable to adapt the target data to solve a downstream task. So this is the input transformation step. And then we will basically pass this transform input, right, this appended data, right, to the pre-trained model, right? And by default, the model will generate a prediction of the classes on the source domain task, right, the ImageNet label space. So the next step we need to do is we need to map the source label to the target label. Here, mapping the ImageNet labels to the downstream label space, right? In this case, whether to predict is ASD versus non-ASD, right? A medical image label. So that will constitute a forward pass. The final step is we need to train the associated parameters in step 1 or step 2 to minimize the training loss on the target domain task. And this training, right, can be if it's a white box setting, right, the training can be simply use gradients, right? You just do back propagation and optimize the performance to find the best weights, right? When we for the parameters in step 1 and step 2. If it's a black box model, then we can do some gradient-free optimization or some black box learning techniques, right? Like zeroth-order optimization to help us find the best set of parameters to optimize the loss evaluated on the target domain task. So in the whole process, one thing to note is that we never fine-tune the weights associated with this pre-trained source model, right? We only play with the inputs and outputs of the model to be able to solve the downstream task. So that is the major difference to standard transfer learning techniques. So just give you more details and more concrete definition about how this reprogramming idea works, right? So we are given a pre-trained classifier, and we call it F, right? So it takes any input in the space of the X, right, the data input space, and then it generates some probability predictions on the output of the space of K, right? K is the number of classes for the target domain task, right? For example, in the ASD case, right, the K equals to 2, right? Because it's a binary classification task. And then the data inputs, right, without loss of generality, we will assume the target data has a dimension D prime, which is smaller than the original source domain dimension D, right? And back to the example that I just provided, right? D is the dimension of the ImageNet pixel numbers, and D prime, right, is the pixel number for the downstream target image. And we assume D prime smaller than D, right? Because we doing so allows extra space to be appended to any downstream data, right? So we allow some spaces to train what we call a visual prompt or input transformation function. And this appended prompts is actually associated with the parameter W, right? So it's basically a universal trainable perturbation W, right? Or if you can also think about it as some visual prompt or some input level prompts that can be tunable and learnable, right, to help us adapt the foundation model to solve the downstream task associated with the parameter W. So how this W is associated with the input transformation is that we will take a target domain data and then apply zero padding, right, to create the same size as the ImageNet inputs. And then we will, for every data TI, right, we will apply the same prompt tuning, right, like a P, right? And then this P is actually it's a function of W and M, and W is the parameters that we want to introduce. And M is the binary mask indicating where the perturbation should be added to the zero padded image, right? So, for example, if we only add the perturbations to the peripheral of the image, right, then it's basically a binary matrix with 1 on the peripheral and 0 for where the target image was placed in the zero padded image. And it's 10H, right? Just to make sure the perturbations is transformed into the space of -1 and 1, right? So it matches with the input pixel range of the target data. Okay, so this is the input transformation step. And the second step is the output label mapping step, right? So we need to figure out a way and design different strategies to map the ImageNet space to the ASD versus non-ASD space. So there are several things we can do here, right? And it can be a non-parametric mapping, or it can be a parametric mapping. So for non-parametric mapping, right, we can be simple as some random label mapping by saying, okay, the prediction probability of ASD, right, is going to be the average of the prediction probability of the several source labels, right? For example, I'm going to say the prediction probability of ASD is going to be the average prediction of Tench plus golden fish plus hammerhead, right? Basically mapping these 3 source labels to mapping these 3 ImageNet source labels to the target label ASD. Or we can do some more specific or more advanced mapping, right? Even introduce a fully connected layer, right? Just to learn how to map the source labels to the downstream label. So this, and instead of random mapping, right, we can also assign some frequency-based mapping, right, by basically passing the zero padded data into the model and check which how do we map the model in the sense that the natural responses of the source label actually resonates the downstream label, right? And doing this frequency-based mapping more or less actually improves the model performance if we can figure out before we start to learn to do reprogramming what is the best natural matching source and label the label mapping between the source domain and the target domain. Okay, so once we have the input transformation set up and also the output label mapping strategy being determined, the remaining thing, right, is to train those parameters associated with these two steps with some task-specific training loss, right? So here it can be as simple as some cross entropy minimization task or some maximizing log likelihood or some weighted version of the log likelihood, for example, the focal loss, right, which is basically a loss that take into account the confidence of the prediction of each class label, and it also includes the standard cross entropy as a special case. But using whatever loss you prefer on the downstream task, right? The remaining thing is to optimize those parameters in step 1 and step 2, right? Using some gradient-based methods or some black box optimization method that can give you some update strategy for the parameters, right? But either way, right, we will obtain a reprogrammed model to be able to learn to predict the classification label in the downstream task. So the whole process can actually be generalized, right, across domains and across models. So for example, right, the algorithm that we designed specifically for image classification can actually be generalized in the sense that we can take a pre-trained source model from any domain and given a target domain data set, again, in any domain. And then we randomly initialize as theta and w, right? So these theta and w are actually the parameters associated with the input and output layers that we inserted for reprogramming. And then we need to transform the raw target domain data input, right? For example, here, this is exactly how this zero padding is being done, and actually how can we introduce a trainable perturbation, right, acting as the input level prompt. We also need to determine how can we map the source label to the target label, right? So the model can be used to predict the predictions on the target domain. And then we need to specify how can we train the model, right? What kind of task loss are we going to optimize theta and w on and evaluate it on the target data, right? And then finally we train the parameters, right, using the loss we specified, and eventually we will obtain a reprogrammed model, right, by using the input transformation and output mapping that we designed and optimized, right, to do reprogramming. So this algorithm is actually very generic and works on different scenarios, depending on what is the right input transformation and right output mapping function that we should use case by case. Okay, so I'm going to show you some examples of how model reprogramming work, right? The first example is this image to biomedical measurements, right? The ASD classification that we have been used as an illustrating example. So here we take some pre-trained model from ImageNet, right? Like ResNet, Inception V3, DenseNet, and so on. And we tried on several medical image classification tasks, right? Like basically these are all medical images related to health diagnostic. We also, because we can also reprogram a black box APIs, right? So we also try to reprogram two APIs, Clarifai.com and Microsoft Custom Vision API. Okay, so we also compare to several baselines, right? And the first baseline is what we call the Medina reprogramming, or Medina adversarial reprogramming, right? Basically, assuming the model is a white box, so you can use the gradient to optimize the reprogramming parameters. We also try to compare to transfer learning with fine-tuning, right? Like fine-tuning the last few layers of the pre-trained model to adapt to the downstream task. And the other baseline is training from scratch, right? So instead of using pre-trained weights, we are just using the same architecture, but with random initialization to train the model from scratch. And we also report state-of-the-art methods that has been achieved in each task. So now going back to the ASD classification case, right? It's actually a low resource setting where we have about 500 images for each class. And this ASD image is actually a 200 by 200 brain region correlation graph obtained from fMRI measurements. It's actually a very noisy measurement. So when we look at the reprogramming results, the fine-tuning results using different cases, right? AR means the white box reprogramming, and BAR means black box reprogramming. So we can observe that no matter what model we choose, reprogramming is actually have the best performance compared to other baselines, right? Like training from scratch and transfer learning, they usually get some accuracy close to random because the data are only 500, and then the model is relatively large, and the task is actually not easy to train and learn. But more interesting, right? So using this reprogramming as a framework to do classification in this case actually already outperformed two state-of-the-art methods, right? And these state-of-the-art methods are actually focused on developing a lot of complicated and manually feature engineering strategies, right? Just to be able to solve the tasks for just to be able to improve the accuracy for this specific task. But with reprogramming and without looking into this sophisticated data augmentation and hand design rules, right, we can already achieve better performance than the reported state-of-the-art. So the same setting also holds for two other data sets, right? Like the diabetic retinopathy detection is also another example, right, where we can see that the reprogramming again has a better performance than state-of-the-art. And white box and black box reprogramming, usually white box will perform a little bit better because it can access to the actual gradients. And for black box reprogramming, we are using approximate gradients instead of a real gradient. So there's a small performance gap, right? But usually they work pretty much better and more efficient than these standard transfer learning baselines. This is the third example, the melanoma detection, right? So we see the same trend here. Okay, so I also want to show this very interesting case where we actually study how can we reprogram online API, right, to do this ASD classification task. So we try this idea on Microsoft Custom Vision API. So this API is one of those AutoML API that allows us to upload a labeled data set, and then they will train a model on our behalf, right, without telling the user what is the model that is being tuned and used, right, to do this inference, right? So they will return API for us to use, but they will not tell us what the model look like. So we use this black box reprogramming idea, right, to reprogram this API to solve ASD classification. So we can see that if you spend like $20, right, just simply to train the parameters we introduce to the API, right, attaching the input and output layers, right, to fine tune the API to do the downstream classification task. We can achieve like 67.8% accuracy for the ASD classification problem when the source model is a traffic sign classifier that the Microsoft Custom Vision API trained for us. This is another example, the Clarify.com, right? So here we can reprogram a not so safe for work API to do ASD classification. So again, we can see that, you know, if you spend like 20 to 30 US dollars, right, by querying the API iteratively to train the parameters, we can actually get okay accuracy to solve these three medical image classification tasks, which is a very good news, right? That means it allows a very cost efficient and simple efficient way to reuse or leverage existing model inference services, right? Those black box APIs, right, to solve a new problem, a new domain that requires a new classifier, but we never need to train from scratch, right, or build things from scratch. We can reuse these existing capabilities, existing pre-trained models to help us do this job at scale and also at the lower cost. The second example, which I believe is very interesting to most of the attendees here, is the applications of speech models. And this is also a joint work with Huck, right? So here we are interested in, given a lot of pre-trained speech models, right here, the acoustic models that are available out there, right? So how are we able to reuse them, right, to solve different tasks, and especially for time series classification tasks. So time series and speech in high level, right, they can also be viewed as some one-dimensional time varying signals, right? But they lie on very different domains, right? So normally people wouldn't consider, repurpose a speech model to do time series classification. And by time series, I mean like sensor measurement classification tasks or ECG, EEG type classification tasks. But with reprogramming, right, these things become very easy and can be done in a principal way, right? So we take a pre-trained acoustic model, right, where the original task, right, is to given a speech input, right, we will generate a voice command prediction for the input speech. So using this pre-trained acoustic model, right, and then what we do is again insert two layers, right, one in front of the model, one after the model, right, for input transformation and also output label mapping to enable this reprogramming speech model to solve time series classification task. So I won't go through the algorithm again, right? This is basically one instantiation of the general algorithm that we just described. And architecture-wise, we are exactly inserting, the input transformation layer and output mapping layer, and make the rest of the pre-trained model fixed in order to adapt this speech model to solve a downstream task. So this figure basically shows what are the layers that we inserted, right, and only train those layers when we do reprogram. And by doing so, we can already show that on a standard benchmark, right, which is called the UCR time series classification task, which contains 30 different time series classification problems, and usually the training size ranges from like tens of samples to up to thousands of samples, depending on different data sets in this benchmark. We see that the voice to series algorithm that we propose, right, on 19 out of the 30 tasks, we achieve similar or better accuracy compared to the state-of-the-art results, which is very encouraging, right, because usually they do this divide and conquer approach for different data sets. They will invent different methods and report best accuracy among all those different methods. But here we are using a principal approach to achieve better results, right, without switching one method, one data set, one method. Here we are using a more unified or foundation way of doing this time series classification. And this is the breakout of the summary I just gave, right, how the accuracy varies across data sets, and in most cases, right, the reprogramming methods, the V2S approach actually outperforms the best results that has been reported on the corresponding data set, and also is much better than the transfer learning approach. Okay, the last example, which I believe is also of high interest to the audience here, is how do we reprogram a language model to do molecule learning. So by language models, I literally mean like those language like text-based language models, right? So those are like a language model. They can take a text sequence and then learn to do different tasks, right? Like for example, question answering, sentiment classification, and so on. But we are interested in reusing these models to solve molecule learning problems. So we basically view molecules, right, like chemicals or materials, right, as some sequence of chemical symbols or chemical representations. For example, a protein, right, can be expressed as a sequence of amino acids, right, or there are some domain-specific strings to describe that protein sequence. For example, something called the SMILE string, right? So it's one way of converting a protein sequence into some descriptions capturing the chemical relations and chemical symbols of the protein sequence. And by using the fact that the language, right, is a text sequence and molecules is some chemical specific sequence, the remaining thing is how can we reuse, right, reprogram a language model to solve these molecule sequence learning problems. And here the techniques that we are using is actually called dictionary learning. So the idea is like this, right? So we already have a pre-trained language model, right? And we are also given a set of protein sequence that we want to learn to classify. So the high level idea is, are we able to represent some protein sequence tokens, right? For example, amino acid token as a linear combination of the token embeddings from the text domain, right? For example, I would like to learn how to represent a protein sequence token as a linear combination of the token embeddings from the source domain, right? So we are going to introduce some parameter theta that is a learnable parameter, which is basically learns how do we linearly combine the set of the token embeddings in the source vocabulary to be able to best represent the target data's token embedding. And then once we establish this linear relationship between the target domain sequence and also the source domain tokens, we can again train this theta, right? This linear combination coefficients using some task-specific loss to minimize the loss and reprogram the model to solve the downstream task. And specifically, this theta, right, is basically learned and updated using some dictionary learning algorithms, right, to make sure we can have a sparse representation in terms of the theta, the linear coefficients, to make it sparse, right? And also to better select what are the key features mapping from the source embedding to the target embedding to enable this cross-modal, cross-domain learning problems. So with this framework, we are able to reprogram like English BERT model to solve different downstream protein sequence learning problems, right? Ranging from secondary structure prediction, stability prediction, solubility prediction, toxicity prediction, right? And so on, right? Because these different tasks, right? They all have their own data sets, but all those data sets are basically can be expressed in terms of one kind of the sequence representations that can be reprogrammed by the English pre-trained language model. So just quickly show you how this model works, right? How this method works. So what the method, what we call is R2DL, works compared to the StelVR methods. And here by StelVR, we compare to some domain-specific foundation models trained on the protein data, as well as some supervised training models, right? When we train the same model from scratch without using pre-training. So one thing to note is that with our reprogramming, we can actually get the comparable accuracy to some in-domain foundation model that requires a large-scale pre-training. So if we compare data efficiency, right, basically the accuracy divided by the number of pre-trained data you require for the solving the protein tasks, right? We can see that our method R2DL is actually most data efficient, right? Because we don't need to access to a large amount of pre-trained data for protein sequences. All we need is to take the label data in the fine-tuning stage, right, to enable to obtain a high performance and high accurate protein sequence learning model. We can also study the data scalability, right, in terms of varying what is the percentage of the training data we have in the fine-tuning stage. And we can see that there is a consistent gap between reprogramming versus pre-trained or even supervised learning tasks, right? So usually in the data limited regimes, reprogramming is actually even more powerful than these standard fine-tuning techniques. It's the high-level takeaway. Okay. So beyond just reprogramming a language model to do classification tasks, we can actually also reprogram a language model to do generative tasks for proteins, right? So this is one example of reprogramming a BERT model to generate new antibodies, right? So by generate, I mean in antibodies, what we do in practice is we will mask some parts of the antibody and ask a model to infill those missing parts, like I showed here. For example, right, finding a better antibody that will bind better to antigens. Right? In this case, we need to mask some parts and ask the model to generate other candidates that can actually provide a better binding. So again, we see the same pattern, right? So how do we reprogram a BERT model to do so? We basically again introduce two layers, right? In front and after the pre-trained BERT model, and use that to repurpose the BERT model to generate the in-field sequences for proteins. So using that, what we observe is that this reprogrammed BERT model actually gives high and accurate recovery rate, as well as a high diversity for the sequence it generates, right? Which is actually very important because we want this sequence to be diverse, so we can test out and find alternative candidates, right? Instead of only looking at the high and like highly similar and repetitive candidates when we are using this model to generate new antibody sequences. And this reprogrammed BERT actually performs much better than some in-domain trained BERT model, like a prod BERT model. Okay, so right now you may wonder like, oh, how what model reprogramming works, right? Why this can be so successful? So together with Hawk, right, in our B2S paper, we actually also provide some theoretical analysis and explanation on why reprogramming works. So the high-level idea is that it's not only about the knowledge transfer, right? Because in transfer learning, people believe that in order to do transfer learning, you have to assume there is some common knowledge between the source model and target model. But we don't think this theory is sufficient, right, for reprogramming. The reason is that we are actually doing cross-domain or cross-model learning, right? So we can do very good reprogramming by repurposing speech model to do time series classification. But it's very difficult to argue what is the similar knowledge, right, that can be transferred from speech to sensor classification, for example. So there must be something else, right? Something more fundamental that enables this reprogramming. So we actually provide a theoretical framework to prove that the risk on the target task, right? And you can think about this risk as some loss function on the target task. It can actually be bounded by two terms when you do reprogramming. The first one is the source risk. Basically, how accurate your source model is on its own source task, right? For example, a better model in the source task will give a lower source risk in this case. And the second term, right, which is actually very important to explain reprogramming, is this what we call the representation alignment loss. It basically describes how well you can align the target data with this input transformation and output mapping function to the source representations, right? So a better alignment can actually, so for example, right, if we want to, the downstream task is a cat and dog classification task. And if you can show that reprogramming, right, can realign the dog and cat data representation to something that is identical to the source data representations, then we can basically reuse the classification rules in the source domain to classify the cat and dog, right, the downstream task perfectly, if the representation can be perfectly aligned. And in this case, right, this representation loss is exactly zero, and therefore we can show that the target risk, right, the bound is actually no worse than the source loss if we have a perfect alignment. So just to show you how this works in terms of the experiments, right? So we look into one example of reprogramming, the voice to series case, right? So we look at the training epochs, right? So when the test accuracy becomes high and saturates, of course the test loss becomes small. But also very interestingly, when you compare the representations of the source data versus the reprogrammed target data, their distance, right, were actually being minimized implicitly while we are doing this reprogramming, which basically says that implicitly the model, when we do reprogramming, the model is trying to learn how to align the target data to the source data representations using the input transformation and output mapping function that we assigned. And this is just some data visualization to show how different methods, right, work and reuse the model in different ways, right? Like before reprogramming, the target domain visual representations are pretty much mixed, right? Which means any linear classification will give low accuracy. And if you use standard transfer learning, right, so it gives some level of separation, but not perfect. But with reprogramming, right, you can always separate the representations between different classes. And the same thing holds, right, if you go to another data set with more number of classes. Okay, so this is the theory, and I'm going to skip it. So the other important topic in this talk is trustworthy AI. Right? So here, I'm going to quickly show you some examples that we have about how can we apply reprogramming to do different trust AI related tasks. So one example is calibration. So calibration is very important for uncertainty quantification, right? So we all know that the neural network tends to be overly confident, right? Which means if your test accuracy is only sorry, if your test accuracy is only 60%, right? But when you look at the prediction confidence of the test images, the model will usually say 80% confidence. And that basically means the model is not well calibrated, right? You have a 60% accuracy in average, but your confidence of the prediction is 80%. So in calibration, what people will do is they will adjust the prediction confidence of the model such that the accuracy will match the confidence to make the model adjust the uncertainty quantification of the model to make it more useful in a lot of trustworthy AI-related applications. So we can also look into how reprogramming can be useful in this case, right? So here we are again inserting two major functions to enable this calibration. The first thing is we insert a universal learnable token at input, and also we use this temperature scaling at the output, which is basically a softmax function with some learnable temperature T that transforms the prediction probability of the softmax function, right, to be able to modify the output prediction confidence. So the training is pretty much like a reprogramming, but at the end, right, we are able to calibrate the model, right, to have a similar accuracy, but lower calibration error, which means a better accuracy that reflects the actual confidence of the model. And it's actually much better than temperature scaling, which means you only calibrate the output, but you don't calibrate the input. And if we use reprogramming, like calibrate both input and output at the same time, we can actually improve the model calibration performance by a lot. So that's a very important use of reprogramming in the domain of trustworthy AI. We also study how reprogramming can be beneficial to differential private fine-tuning, related to differential privacy. So the setting here is that we start from some pre-trained model, right? Pre-trained on public data, public and non-private data. And then we are going to take private data with this public pre-trained model weights as a starting point to fine-tune our model with differential privacy budgets, right? So the differential privacy here is actually the typical epsilon delta differential private guarantee, which means for two data sets, right, differ by 1 point, actually you are required to make sure your model outputs, right, is actually bounded by this epsilon exponential of epsilon plus some delta, right, to make sure if the model differs by 1 point, the output can also be the difference of the model needs to be bounded, right, to ensure a certain level of differential privacy. So with this in mind, right, we can study different fine-tuning methods, right? How well the accuracy, privacy, utility trade-off can be, right? We can use reprogramming or use any full fine-tuning, partial fine-tuning to do this differential privacy fine-tuning strategies. And we can also study both the centralized setting, right, where you only have one model, right, versus the federated setting, right, where you have multiple models. Multiple clients that want to jointly train a global federated model, and each client will initialize their own local version of the reprogrammable modules, right? Like these local CWs here, and only exchange those trainable parts to do this reprogramming in the federated learning setting. So the performance turns out to be great, right? So if you compare different parameter efficient, if you compare to different fine-tuning methods, right, not necessarily parameter efficient, we can observe that when we vary epsilon, right, the level of data privacy we want to achieve, actually model reprogramming gives the best accuracy across all the epsilons that we tested, right? Because which basically says we can use reprogramming, right, to further improve the accuracy privacy trade-off, right? Given the same privacy budget, reprogramming can train a more accurate model compared to partial fine-tuning, full fine-tuning, and training from scratch in both centralized and federated learning settings. we can also apply these techniques, right, to foundation models, right? Like basically use this differential aware method, right, to learn differential private visual prompting to reprogram a foundational visual model to solve a downstream classification task. So in the interest of time, I wouldn't talk too much about how this was done, but it's basically applying reprogramming with some state-of-the-art differential private aware training method called PATE, private aggregation of teacher ensembles. I believe Hak will also talk about that in his slide if he has not done so already. So using this prompting and PATE idea in a differential private setting, what we observe is that given the same epsilon budget, right, with epsilon budget equals to 2, for example, our methods can obtain a CVAR10 accuracy as high as 97.16%, which is actually very close to the best accuracy you can get without any data privacy constraint. Basically saying the gap between non-private and private privacy-aware training is has been made very, very small with reprogramming ideas. And of course, the pre-trained model plays a very key role here, right? So if you switch different backbones of the pre-trained model, we see some variations at the output, the final accuracy on the downstream task, which is again validates the theory that we have, right? By saying, okay, in order to have a better performance on the downstream task, you need to make sure you are using a more powerful source model. And in some cross-domain settings, right, for example, reprogramming ImageNet classifier to do some block and mist, right? Again, medical image-related applications, we see an even larger performance gain to use this reprogramming because of these cross-modal learning capabilities compared to these transfer learning approaches. Okay, so I would like to quickly provide some takeaways, right? So in this section, I introduce you a very, interesting and powerful technique called the model reprogramming. So in general, you can think about this as a new paradigm to do resource-efficient cross-domain learning with some large pre-trained models. And the reason we want to do that, right, is we want to improve data efficiency, right? If you only have a few samples at hand, right, don't panic, right? You can use reprogramming and borrow any pre-trained model from different domains, right, to solve the downstream task efficiently. And also, we show a lot of empirical use cases and studies which turns out to be very successful in terms of reprogramming images to image models to solve medical image classification tasks, reprogramming speech models to solve time series learning problems, and reprogramming language models to solve molecular learning tasks. Also, there are some specific applications in trustworthy AI domain, right, such as privacy constraint fine-tuning. And that it basically shows reprogramming can work pretty well with any existing differential private training methods, right, like DPSGD or PATE, as long as you can specify which layers to insert some layers and only train those layers with reprogramming and DP-aware training methods. I also show some use cases in uncertainty calibration and quantification. And also we briefly talk about what is the rationale behind the success of reprogramming through a theoretical analysis. So if you are interested in reprogramming, right, we open source several codes just to the community, right, to help you get a quick start with reprogramming in your own task. And I also listed some references related to the talks that I presented today. And I'm ready to open the floor for questions. And if not, we can also talk more about that in the Q&A session. And although I may not be able to attend, feel free to ask Hak, who is also on many of the papers and works that I just presented. Thank you for your time and patience. Any questions, comments?
All right, so thank you, Pingyu, for the presentation. I think we can allow, and for audience, please come to the stage directly. So then you can hear you from the mic. And the second, please pick the line. Maybe.
Right, just come here, yeah. Hi, this was pretty cool. I have kind of a technical question. Um,
Sure.
in all of these comparisons, did you also make sure that the fine-tuned model beat a model with no kind of frozen model in the middle, and also a randomly initialized model in the middle? So just the architecture, not the pre-training.
Oh, sorry, I didn't get your question complete. So you're saying, I think what in the middle?
If I've understood correctly, you're reporting results from the result of adding some stuff onto a pre-trained model,
Yes.
right?
Yes.
So did you also check that your results you reported are better than what you would get if you took out the model in the middle and just used the probe, or randomize the weights of the model in the middle?
Oh,
So
yeah,
just use their.
Okay. I see. Yes. Yeah. So if I understand you correctly, you're asking like, what if I don't use the pre-trained weights, right? Just using the same architecture but train from scratch, right? So that will be like the train from scratch baseline we use here. So it's the same architecture, but you are using a randomized weights instead of the pre-trained weights.
I see. Okay, cool. Thank you.
Yeah, in most cases it's actually better because especially for a few shot like a low data regime, and also if with the data privacy guarantees, training from scratch actually needs more epochs, right, or more data to achieve comparable accuracy. And in those cases, right, reprogramming is actually much better than training from scratch.
Okay, cool. Thank you.
Sure.
Yeah. I see. Okay, cool. Thank you.
So thanks a lot
Hi.
for a great talk. So I have a question regarding the selection of the foundational model. So in your theory, you argue that the knowledge transfer doesn't play much value here. So the question would be, how do you pick the base domain and the base model to do the model reprogramming for a given task?
Yeah. So that is all. So the model selection, right, is always a tricky question. So actually, it's some ongoing work that we are doing. Is actually we also try to provide what the AutoML type of method that we can say, okay, given the set of pre-trained models available, right, and also given the target task, are we able to select the best, the most useful model to solve the downstream task? So it's certainly there are some methods that we are developing that can certainly support that, right? But fundamentally, right, basically what our theory shows and also our empirical results shows is that whatever model you use to solve the downstream task, it's better to be as much powerful model as possible, right? Like the theory I show you basically indicates, right? Like a more the model that can give us a lower loss in the source domain will actually implicitly here. Okay, so a source model that is actually more accurate, right? Basically means a source model that will have a lower loss, right? Will actually make the upper bound of the target loss lower, which means we should always choose the model that is more performant, right? Actually more powerful, more accurate to use. For example, if you ask me to choose a small ResNet versus a more recent Vision Transformer, I will probably choose the Vision Transformer because the Vision Transformer gives a lower accuracy, a lower loss in this task.
Yeah, thanks a lot. So maybe a quick follow-up. So
sure.
Given you have two models from the same domain, it's kind of logical to pick the better one. But I see some sort of a trade-off here between the power of the model and the ease of representation alignment task, right?
Yes.
So you have a very powerful model from a very far domain.
Yes.
And then the question is like, should you go with this or maybe some weaker model, which would be easier to align the data to?
Yeah. That is a very good point. So basically in the auto reprogramming, that's how we call our method that we are developing. It's actually trying to train the different pre-trained model using a few epochs and exactly to what you said, right? Actually check how well they can align the target data in the first few epochs and use that as a proxy to select the best model, right? So without some like a quick training or few shot training, it's actually very difficult to check how well each model aligns the data, right? But like, exactly to your point, high accuracy model, right, sometimes may not do a good job in terms of aligning representation, right? So in practice, right, to choose the best model to do reprogramming, you have to take them both accuracy and also their ability to align representations into consideration. So so I you actually provide a better answer than I do. Yeah, you're right.
Okay, cool. Thanks a lot.
Sure.
No.